All right, you guys, we're going to look at 3-3 today. Usually, this is kind of the doozy of the lesson as far as chapter 3 is concerned. And it doesn't have to be hard, okay? The reason 3-3 is challenging is because number one, it's all word problems. And number two, it's about a 5-step process to actually fully complete. So it's just a lot to remember. Each step in itself, like writing an equation, finding points of intersection, evaluating a function, shading, okay? All of that stuff you've done before and is pretty straightforward when it comes to things. It's just a matter of piecing it all together is kind of the challenge, okay? So first thing we're going to look at is just finding minimum and maximum values, okay? So essentially today is all about optimization and linear programming. So what we're trying to do is look at a particular function and figure out what's the highest or lowest value. How this would kind of play out in terms of business when you're thinking about things like you know business is trying to maximize profit and minimize cost. So today we're going to look at basically simplified examples of this process. Obviously, in a million or billion-dollar business, there's going to be a lot more facets to it than a few lines or a few limitations, but you'll kind of get the general idea. So linear programming is a method for finding the max or minimum value given specific constraints, okay? Looking at these two situations, these are two situations that it could occur. Our constraints are the lines. Those are the limitations. So if I'm looking at a company, those are, the hours of labor. Those are the times machines can run. Those are your manufacturing supplies that are in stock. Those are the, just products in general or demand that people need, okay? So all of those constraints are limitations set by the problem, okay? Within those constraints, you have what's called your feasible region. And any point in your feasible region is satisfied by all of your constraints. Same with a feasible region that's unbounded, okay? So all of these points are satisfied by those constraints. Any of them will work in the problem. The purpose of this, again, is to find not just a point that works, but we want to find the maximum or minimum value, okay? With a bounded region at your vertices, these are where the maximum and minimum values occur. With a bounded graph, your maximum and minimum value will always occur at the vertex of a feasible region. Again, both a maximum and minimum value will occur at a vertex. With your unbounded regions, these are slightly different. You'll have either a maximum or minimum. Since your region is going to go on and continue forever, there's either going to be a maximum and no minimum or a minimum and no maximum. So you just kind of want to keep that in mind as we go through things. And we're just going to dive right into the first example. So kind of looking up here, we have a set of 3 constraints in this problem. You can tell your constraints because they're always inequalities. All right, so we have our 3 constraints here. I am going to first graph my constraints and try to figure out my feasible region. Is it bounded? Is it unbounded? So I'm going to graph -2 and 6. 1, 2, 3, 4, 5, 6. All right. And then if we're kind of keeping track, our blue line, we're going to shade between. I'm just going to make note of that so I kind of remember because I'm going to shade at the very end. Our Y values, we have a horizontal line at 1, 2, 3, 4, and 5. And again, we're going to shade between these, just kind of making note of that. And then I have the line Y is less than or equal to X plus 3. So my Y-intercept is 3, and my slope is 1. So I'm going to go up 1 over 1, or down 1 to the left 1. And now the question is, which region am I going to shade? Well, I see that y's are less than, so I need to shade below my line in red. So my feasible region between the blues, between the greens, and below the red is going to be there. So that's step number one when we're looking for this bounded region, is we need to graph our constraints, okay? So that's the first part. The second part says name the vertices of your feasible region. If you guys are using graph paper and being very particular, it's going to be super great. What was that? Ooh, interesting. It's going to be super important that your graphs are pretty consistent. Again, if I use graph paper, it's really easy to see. I have vertices at -2, 1. I have vertices at 2, 1, 2, 3, 4, 5. I have a vertice at, what is that, 6, 5. And I have a vertice at 6, 1. All right. So name the coordinates of the vertices we just finished. Now we need to find the maximum and minimums, okay? And this is the function I'm going to use, okay? So essentially what I need to do is I need to plug in 2, 1. I need to plug in 2, 5. I need to plug in 6, 5. And I need to plug in 6, 1 to this function to see what values I get. When I plug in -2, -1, I get 10 plus 2, which is going to be 12. When I plug in 2, 5, I get -10 and +10, which is 0. When I plug in 6, 5, I get -30 plus 10 is going to be -20. And at 6, 1, I get -30 and +2, which is -28. So after we've kind of evaluated these based on the function, you can see that 12 is the max value and 28 or -28 is the minimum. Okay, so to kind of further clarify what's going on here, like we said, all of these points in my bounded region work in terms of my constraints. They're all solutions to my constraints. But if I were to plug in any of those points in black into this function, they will never be higher than 12, and they will never be lower than -28. All right? And that's kind of what we're looking at today. Again, sorry, this is kind of a long-winded lesson, okay? Continuing on with example 2, we're going to do the same thing we just did. I'm going to change the scale slightly. So I'm going to go by 2s, 2, 4, 6, 8. And I'm going to shade below this line. So again, we're going through the same process, except you'll notice this region is going to be unbounded. So we have -x plus 4. So y-intercept is 4. And then we're going -x down 2 over 2. We'll say that's by 2s as well, just to keep my graph consistent. And we are going to shade, if you notice, above the line in green. We'll continue on with our red line. Our y-intercept is 10, 2, 4, 6, 8, 10. It also has that slope of -x. So I'm going to kind of keep drawing that region there. And if you notice, we have 2 parallel lines. So we have what's called an unbounded region. So we're below the red, above the green, and below the blue. Okay. So we graphed our system, named the vertices. Well, again, conveniently, if our graphs are pretty to scale, we're going to find points at 2, 8, and negative 4, 8. And those are the points in your region you want to test. So again, we have 2, 8 and negative 4, 8. We're going to plug these into the function and solve. When I plug in 2 8s, I get negative 12 and positive 64, which gives me 52. When I plug in negative 4, 8, I get positive 24 and positive 64, which is 88. So now the question on unbounded regions becomes, is 52 the minimum or is 88 the maximum? Okay. So to figure this out, remember, like I said before, all of these points in the region are satisfied by the constraints. Okay. And what we're going to do is we're going to pick one of these to test. So let's say I test, and the trick with testing is to move, far out in your region, okay? Just to kind of get away from those 2 points, because if you pick a point kind of up here closer, you actually might end up between 52 and 88. And if you wind up between the two, you still don't know if 52 is low or 88 is the high. So what we're going to do is we're going to test. It looks like I picked, what is it, 8, 0. And we're going to see. So when we test 8, 0 into our function, we get the function's value is negative 48. Okay. So as we look at this, if we picked a point way out here in my region and got negative 48, as I move through my region, what does this number tell us? If you notice, that tells us that the numbers, since it's smaller than 52, are going to keep getting smaller as I move throughout my region, which means 88 must be the maximum. Okay. So again, unbounded regions, we do everything the exact same, but you want to test a point to figure out whether each of your values are either the maximum or the minimum. And just make sure your test point is, a ways or through your region, because if it's between 52 and 88, again, you got to pick another point because you don't know yet whether it's the max or minimum. All right. Here we go. This is for all the marbles, the optimization process, okay? So we're going to put everything together. You'll notice that I have everything kind of broken down by steps. So it is a 5-step process. And again, each step isn't super challenging in itself, okay? So we're looking at a landscape company. They mow lawns and prune shrubbery. The company schedules 1 hour for mowing lawns and 3 hours for pruning jobs. Each crew is scheduled for no more. So sorry, I probably should be underlining as we go through things. Each crew is scheduled for no more than 2 pruning jobs per day. Each crew is set up for a maximum of 9 hours per day. On average, they charge $50 for mowing and $140 for pruning shrubs, okay? The last sentence generally in your problem is the absolute most important. It says, find a combination of mowing lawns and pruning shrubs that will maximize the income. As soon as you see the word maximize or minimize, that is what your objective function is based on, okay? So I need to come up with a function, and I'm going to call it mowing and pruning. A function based on mowing and pruning that's going to maximize my income. Well, if I sift back through the problems, I remember that I charge $50 for mowing and $140 for pruning. So you have now just successfully completed step 1 in the problem. We are trying to maximize the amount of money my company makes. Okay. Step 2 is going to be coming up with our constraints or limitations set by the problem. If we go back through the problem, we'll notice there was a number of constraints and limitations based on things. Well, if we go right here, it takes 1 hour to mow and 3 hours to prune. So I know that mowing takes me 1 hour, pruning takes me 3 hours, and I have a maximum of 9 hours per day. So my crew can mow and prune, but they can't work over 9 hours a day. Another limitation here, it looks like we can do no more than 2 pruning jobs per day. That means pruning must be between 0 and 2. Okay. And then the last constraint we want to kind of put into place is implied in the problem, but we want to make sure our M is greater than or equal to 0. Okay, we can't have a negative number of mowing jobs. That's not going to make sense. Okay, then from here, we're going to graph our constraints. Okay, and to save you a little time, I thought I had a graph. I don't know where my graph is. So we're going to have to just do a little chicken scratch here. Okay, so try to be pretty clear with my points. Oh wait, I should have done 9 on the x-axis, sorry. It would help if I actually had a graph here. 1, 2, 3, 5, 6, 7, 8, 9. 1, 2, 3, 4, 7, 8, 9. Then we'll go to town. Okay. So my first line, I need to graph those constraints. So if I plug in M and P, all right, P would have to be 3. M would have to be 9 for my equation to work. And then I'm actually going to kind of plug in these points. So if I were to graph that or put that in slope-intercept form, I know that my slope is going to be negative 1/3. And I'm going to kind of highlight those points to help me along. I also have the line between 0 and 2. And finally, I have greater than 0, which is this way. So we want to come up with my region. I'm between the greens. I'm to the right of the red. And it looks like I need to be below the blue line. Again, if it's not entirely clear where your vertices are, you can solve the system. Otherwise, hopefully your graphs are pretty consistent. So we have 9, 0. Looks like we have 3, 2. We have 0, 2. And we have the final vertex at 0, 0. So those are the points of my feasible region: 0, 0, 0, 2, 3, 2, and 9, 0. Okay. Now we need to test them. We want to figure out how to maximize the profits again. So I'm using the function we originally started with to figure out my max profit. Okay. 0, 0. We know if I don't do anything, I'm not going to make any money. So that one's pretty easy. All right. If I don't mow, but I prune twice, I am going to make $280. If I mow 3 times and prune twice, I am going to make $430. And then my last option is I mow and I don't do any pruning. 9 times 50 is $450. So looking at this situation, if we're trying to maximize profits of the company, bam, right there, we need to mow 9 lawns and we're going to make $450. Heck yeah, I would take that for a day's work. So that's the process, okay? So optimization, again, we set up our objective function, we figure out the limitations, we graph those limitations, we find the points, and then we evaluate them. Again, each step in itself is not